Hey YouTube, in this tutorial you're gonna learn how to control position of a stepper motor with STM32F103C8. Here I'm gonna use TB6600 driver, but for STM32 code it doesn't matter which driver you're using. To control a stepper position you have to generate a specified number of pulses with STM32, and that's exactly what I'm gonna teach you. This is the first tutorial on YouTube that teaches you how to generate a specified number of pulses with two STM32 timers in non-blocking mode with minimum CPU load. CPU is just gonna start the operation and there's not gonna be a delay in our code. I'm gonna use two timers in bidirectional master slave mode. Let's start with motor and driver. This is the motor that I'm using, and for driver configuration there are 6 dip switches on TB6600 for limiting current and setting macro steps. To have the highest resolution I set 32 micro steps. It means for motor shaft to rotate 360 degrees I have to give driver 6400 pulses, and because rated current for the motor is 1.4 amp I set 1.2 as peak current in current setting. So dip switches are off, 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 on, off, on. This is the schematic. To control the driver there are 3 pins which are isolated with 3 optocouplers that are inside the driver. I don't need EN pin. Pulse plus and direction plus are connected to 3.3. Direction minus is connected to PS7, which is a GPIO and controls direction of rotation. Pulse plus is connected to PS6, which is timer 3 channel 1 output. I'm going to generate pulses on this pin. STM32 job is going to be generating pulses on PS6 pin with timer 3 channel 1 output and set or clearing PS7 to determine clockwise or counterclockwise rotation. Timer 3 channel 1 output frequency specifies shaft speed, and timer 3 channel 1 number of output pulses specifies position. In the next video I'm gonna talk about variable speed and changing frequency. In this one, frequency and motor speed is going to be constant, and this video is just about controlling number of output pulses on timer 3 channel 1 and controlling stepper motor position. For pulses on PS6 duty cycle has to be 50%, and in this video output pulses frequency is constant and it is 5333, which causes motor shaft angular velocity to be 50 rpm. In the next video I'm gonna talk about how can we configure ARR and PSC to change motor speed. In this video PSC is 6749 and ARR is 1, and remember CNT counts from 0 to ARR and ARR is 1, so CNT counts from 0 to 1. It's going to be 0 1 0 1 0 1, and I set CCR 1 to 1, and timer 3 channel 1 output is going to be in PWM mode 2 configuration. It means timer 3 channel 1 output is low when CNT is less than CCR 1. When CNT is 0, timer 3 channel 1 output is 0, it's low. And when CNT is greater or equal to CCR1, timer 3 channel 1 output is going to be high. When CNT is 1, which is equal to CCR1, timer 3 channel 1 output is high. This is 50% duty cycle on timer 3 channel 1 output. Let's start doing the project with configuring GPIOs first. I'm using PS6 and PS7. First, I have to enable GPIO clock by setting IOP AEN bit in RCC APB2 ENR register. PS6 has to be in output alternate function push-pull mode, so mode 6 has to be 10 and CNF6 has to be 102 in GPIO CRL register. PS7 has to be in output general purpose push-pull mode, so mode 7 has to be 10 and CNF7 has to be 00 in GPIO CRL register. This is my project. Here I have CMCs, clock configuration to 72 MHz and system init. System init function does the same job as HAL init function. It's for configuring SysDig, priority grouping, and also serial wire pins. Back to main. In the main.c file I write a function with return type of void. I name it stepper init and input argument is also void. I write the function declaration before main. This is our GPIO configuration. First I set IOP AEN in APB2ENR register to enable GPIO clock. Then I config PS6 pin in output alternate function push-pull mode and PS7 pin in output general purpose push-pull mode. Next step is timer 3 time-based registers configuration. I want to use timer 3. First step is enabling its clock by setting timer 3 EN bit in RCC APB1 ENR register. Then I have to clear 2 CMS bit in timer 3 CR1 register because I want counter to be in edge align mode and I want counter to count up or down. Then I have to clear direction bit because I want counter to count up. I don't need to set other bits in CR1 register in timer 3, so I can clear all bits of timer 3 CR1 register. I talked about values for ARR and PSC and CCR1 before. These are configuration for time base for timer 3. First I enabled the clock, then I clear all bits of CR1 register, then I set ARR, PSC and CCR1. Next step is configuring registers for timer 3 channel 1. Because I want channel 1 to be in PWM output mode, preload has to be enabled by setting OC1 PE bit in CCMR1 register. But when you're enabling preload, channel has not to be in output mode, and that's configured in CC1S bits in CCMR1 register. If CC1S bits both are cleared, channel 1 is in output mode. Because I don't want it to be in output mode, I set both bits of CC1S. In the next step, I enable preload by setting OC1 PE bit in CCMR1 register. In the next step, I'm gonna configure CC1S bits again and clear both these bits because I want channel 1 to be in output mode. Next step is configuring channel 1 in PWM mode 2 by setting 3 bits of OC1M in CCMR1 register. Next step is configuring polarity for channel 1 output in CC1 P bit in CCER register. I set this bit because I want polarity to be active low, and I want to invert the output of channel 1 because it is inverted again by optocouplers in our driver. Next step is enabling channel 1 output by setting CC1E bit in CCER register. These are configurations for channel 1 in PWM inverted output. First I set both bits of CC1S, so channel 1 is not in output mode, so I can enable preload for channel 1. Then I set channel 1 in output mode. Next step is setting all 3 bits of OC1M, so channel 1 is in PWM mode 2. In the next line I cleared CC1P bit in CCER register, so channel 1 output is inverted. In the next line I enable channel 1 output. Compile the code. There are 2 errors. Here I write the wrong definition. This is RCC APB1 ENR. Compile again and there is no error and warning. Now I can test the code. To configure timer 3 channel 1 output to start generating pulses, I just have to set bit CEEN in timer 3 CR1 register. For that I create a function named stepper init with return type of void and input argument of void. In this function I write timer 3 CR1 register. I do bitwise OR assignment with timer CR1 CEN bit. I set CEN bit and now timer is enabled. I put declaration of this function before main. Now in main, first I call stepper init and then stepper start. Compile the code. This is my project. This is the motor. This is 6600 my driver. This is blue pill and this is the ST-Link that I'm use. I use ST-Link. I use ST-Link on Nucleo. This is the power for motor. And these are connections for pin PR6 and PR7 to pulse minus and direction minus. The code is here and now I run the code. As you can see, motor is started rotating. To configure motor shaft to rotate in clockwise or counterclockwise direction, I have to make PR7 output pin low or high. I don't know which is which, so we have to test it. To change PR7 output pin status, I'm gonna use BSRR register in GPIO peripheral. Here I write GPIO arrow operator BSRR register. For making PR7 output status high, I have to write to BS7 bit GPIO BSRR BS7. To make PR7 output low, I have to write in BR7 bit GPIO BSRR assignment GPIO BSRR BR7. Now with these 2 lines I'm gonna create 2 definitions. I cut them from here. I go to block selection mode. I choose 2 lines here. First I write hash define to underline PR7. Then I put a space and paste the code that I wrote. I exit block selection mode. This definition is going to be PR7 high and this one is PR7 low. Now a stepper start function is going to have an input of type uint 8t. Its name is going to be dir, direction. I also need 2 definitions for direction. I enter toggle block selection mode. I choose 2 lines here. First I write hash define to underline dir. One is going to be clockwise and one counterclockwise. Clockwise would have value of 1 and counterclockwise value of 0. Type of both are going to be uint8t. So counterclockwise is 0 and clockwise is 1. I created these two macros for input of this function. In stepper start function, I write a if input of this function, which is dir, equals direction clockwise, then I wanna make pl7 output high, pl7 high. Else I'm gonna make pl7 output low. Correct the declaration of this function. Now stepper start function has one input. First I'm gonna give direction clockwise for input of this function. If motor is not rotating clockwise, I'm gonna change here. I also gonna need another function with the return type of void. I name it stepper stop and input argument is void. In this function, I just want to clear CEN bit in CR1 register so timer 3 stops. Instead of bitwise OR, I write bitwise AND with not of bit mask. I put declaration of stepper stop before main. Now compile the code, there is no error and warning. Here I called stepper start with direction clockwise. Load the code in the microcontroller. As you can see, motor is rotating counterclockwise. Here, instead of pl7 high, I put pl7 low. And down here, I write pl7 high. Compile again and load the code again. The motor is rotating in the wrong direction again, and I figured out that I connect the wrong pins. So now motor is rotating in the right direction, it's clockwise direction. In the next step, I'm gonna start the motor, then there is going to be a delay function with a 5-second delay, and then I'm gonna use a stepper stop, and then rotate the motor in the other direction. Compile the code and load it again. So 5 seconds in clockwise direction, and then it stops and it rotates in the counterclockwise direction. Easy part is done. I started timer 3 to generate pulses, but it has to be stopped after generating a specified number of pulses to control a stepper motor position. Pay attention, each time timer 3 updates, it outputs one pulse. So timer 3 has to be stopped after it updates a specified number of times. We have two problems that we're going to solve. First, we have to be able to count number of timer 3 updates, and after number of updates reached a specified number, timer 3 has to be stopped. I'm going to use timer 1 to count timer 3 update events, and when it reached the specified amount, timer 1 is going to stop timer 3. To achieve this, timer 3 is going to be master of timer 1 and at the same time a slave for timer 1. First, let's talk about how master-slave relation works between two timers. Master timer generates a signal named trigger output or TRGO, and the slave timer receives this signal as input. For a slave timer, this signal is called trigger input or TRGI. To configure each master-slave relation, first how TRGO trigger output signal is generated in master timer. We configure this by MMS bits in timer CR2 register in master timer. Second and third question is about configuring a slave timer. Second question is where trigger input is coming from for a slave timer. This is configured in TS bit in timer SMCR register in a slave timer. And the third question is what trigger input is going to do in a slave timer. This is configured in SMS bits in SMCR register in a slave timer. First problem that is going to be solved by a master-slave relation is counting number of timer 3 update events with timer 1. In the first master-slave relation, timer 3 is master and it's generating TRGO signal, and timer 1 is a slave and receives it. To configure the master-slave relation, we ask the first question, how trigger output is generated in master timer, in this case timer 3. I want timer 1, which is a slave timer, to count number of update events of timer 3. So I choose update event as trigger output in timer 3. MMS bits in CR2 register has to be 010 0. So the update event is selected as trigger output in timer 3, which is the master timer. So in timer 3, every time update event is generated, there is going to be a pulse, and this signal is trigger output for timer 3. Next step is configuring a slave timer, in this case timer 1. We have to ask where trigger input for a slave timer. Trigger input is coming from master timer, which is timer 3. In table 82 in reference manual, you see when a slave timer is timer 1 and trigger output is coming from timer 3, TS bits should be 010. TS bits are in SMCR register in timer 1 peripheral. Pay attention, TS bits configuration is done in a slave timer, which in this case is timer 1. Next step in configuring a slave timer is asking the question what trigger input is going to do in a slave timer, in this case timer 1. I want timer 1 to count how many update events has happened in timer 3. So in SMS bits in SMCR register in timer 1 peripheral, I choose external clock mode 1 configuration. It means rising edge of trigger input is going to clock the counter. This means timer 1 CNT register is going to increment or decrement by 1 with each rising edge of trigger input, which we configured to be timer 3 update event. It means timer 1 CNT register is going to count number of timer 3 update event that has happened. Second problem that is going to be solved by master-slave relation is stopping timer 3 by timer 1. Now timer 1 is master and timer 3 is a slave. But how timer 1 is going to stop timer 3? I configure timer 1 in down counting mode and also in 1 pulse mode. It means timer 1 counter is going to count down from initial value that we write in timer 1 CNT register to 0, and then timer 1 is going to stop and it's not going to count anymore because it's in 1 pulse mode. Remember, clock for timer 1 counter is coming from timer 3. And with each timer 3 update event, timer 1 CNT decreases by 1. Now I want to introduce to you the enable signal. This signal is going to be output trigger TRGO for timer 1. In every timer, there is an enable signal that is high when CEN bit is set. When we set CEN bit in CR1 register, timer starts counting and counter is enabled. Enable signal is low when CEN bit is cleared and counter is disabled. Imagine I want timer 3 to generate 7 pulses. First, I config timer 1 in down counting mode and also in 1 pulse mode. Then I write 6 in timer 1 CNT register. Then I enable both timers by setting CEN bit in their CR1 registers. This is enable signal for timer 1. And before I set CEN bit in timer 1 CR1 register, enable signal is low. When I set CEN bit, enable signal is going to be high. Now with each timer 3 update event, timer 1 CNT decreases by 1. And because timer 1 is in 1 pulse mode, when timer 1 CNT reaches 0, timer 1 counter is going to be disabled and CEN bit gets cleared and enable signal is going to be low. This signal is going to be timer 1 trigger output and timer 3 trigger input for the second master-slave relation that we're going to config so that timer 1 can stop timer 3 after timer 3 generated a specified number of pulses. In the second master-slave relation, first question is how trigger output is generated in master timer, in this case timer 1. I want enable signal to be trigger output in timer 1. So MMS bits in CR2 register in timer 1 has to be 001. So the counter enable signal is used as trigger output. Next we're going to a slave timer, where trigger input for a slave timer, in this case timer 3, is coming from. In table 86 you see when a slave timer is timer 3 and you want master timer to be timer 1, TS bits should be 000. So I have to clear all 3 bits of TS in SMCR register, so trigger input for timer 3 is coming from timer 1. Next question is what trigger input is going to do in a slave timer. I want this trigger input to stop timer 3, so I choose gated mode in SMS bits in SMCR register. In gated mode, the counter clock is only enabled when trigger input is high and counter stops as soon as the trigger becomes low. This trigger input is coming from timer 1 and it's the enable signal in timer 1. After we set CEN bit in timer 1, enable signal is high. This enable signal is trigger input for timer 3, and when it's high, timer 3 counter can count and when it's low, timer 3 counter is going to be disabled and it's not going to count. And this is exactly what I want. I want to be able to stop timer 3 by timer 1, and this is how I'm going to achieve this. So SMS bits in SMCR register in timer 3 has to be 101. So trigger input in timer 3 is able to start and stop timer 3 counter. Master slave configuration is finished. There are other problems that we have to talk about. Question is how many pulses I am able to count with this method. I was going to write number of pulses that I want for timer 3 in timer 1 CNT register, but timer 1 counter can only count from 65,535 to 0, which is approximately 10 rotation. One solution is using 32-bit timers, but they are not available in STM32F103C8. You can use them in some STM32F4 MCUs. Another solution is using repetition counter register in timer 1. There is actually a third solution, and that's another master-slave relation. We can use a third timer to count how many times timer 1 updates, but I'm not gonna talk about it in this video so you don't get crazy. Now I wanna implement solution 2 using repetition counter register. In advanced timers, timer 1 and timer 8, there is a second counter called repetition counter. It's an 8-bit counter that decrements by 1 from reload value that we store in RCR register each time CNT counter overflow or underflows. When repetition counter reaches 0, an update event happens and RCR is going to reload in the counter again. We don't have access to repetition counter itself. We are just able to write the reload value in RCR register. Repetition counter controls the rate in which update event happens. Update event can only happen if repetition counter is 0. Pay attention to these two examples. In the first example, ARR is 6. So CNT counter starts from 0 and increments by 1 with each rising edge of CNT clock. After it reached ARR, counter overflow happens. Again, CNT counter is going to be 0 and it's going to count again. In the normal situation, when RCR is 0, every time counter overflow happens, an update event happens. But when RCR is 1, repetition counter is going to start from 1, and every time counter overflow happens, it's going to decrement by 1. After it reached 0, update event can happen. So update event happens here and here. In the next example, RCR is 2. So repetition counter starts from 2, it decrements by 1 each time counter overflow happens. Here it changed from 2 to 1 and from 1 to 0. And when the reload is going to happen in repetition counter and RCR, which is 2, is going to reload in it again, that's when update event happens. It happens here and here and here. In the normal situation, when RCR is 0, update event happens every time counter overflow happens. In one pulse mode, timer counter is going to get disabled in the next update event. And with repetition counter, we are able to extend counting range of the timer in one pulse mode. In normal situation, when RCR is 0, counter starts from 0 to ARR, then counter overflow happens. At the same time, update event happens, and then counter is going to get disabled and it's not going to count anymore. But when RCR is 2, update event is not going to happen when overflow happens. Repetition counter is going to start from 2. With each counter overflow, it decrements by 1. After it reaches 0, update event happens and now counter is going to stop. This is how I'm going to extend our counting range with repetition counter. So how I'm going to use RCR in our project? I know CNT is gonna start from initial value and count to 0. Then counter is going to underflow RCR times, then it's going to stop. First I want ARR value to be 6399 because I need 6400 pulses for each rotation. And when CNT counts from ARR, which is 6399 to 0, it is 6400 pulses. Now imagine I want 2 1/4 rotation. Number of complete rotations is 2. I write 2 in RCR register. The remaining pulses are 1600. So I write initial value of 1599 in CNT register. CNT is going to count from this value to 0, which is 1600 pulses. And after that, we're gonna have 2 complete rotations. After that, timer is going to stop. And this is how I control number of pulses that I want to generate. It's going to be Q times 6400 plus a reminder. Q is number of complete rotations. I write Q in RCR register and R-1 in CNT register in timer 1. Number of timer 3 output pulses is going to be Q times 6400 plus R. And this is how I specify number of output pulses for timer 3. We also have to do timer 1 time-based registers configuration. Because I want to use timer 1, first we have to enable its clock by setting TIM1 EN bit in APB2 ENR register. CMS bits has to be cleared because I want H align mode and counter is going to count up or down. For timer 1, I want counter to be counting down, so direction bit has to be set. I want timer 1 to be in 1 pulse mode. As you can see, in 1 pulse mode, counter stops counting at the next update event, clearing bit CEN. So OPM bit in CR1 register has to be set. In main.c file in stepper init function, here I paste configuration for timer 1 time base. First I enable timer 1 clock, then I clear CMS bits. In this line, I set direction and OPM bits in CR1 register. Prescaler is 0 because I don't want a pre-scale. Trigger input, which is coming from timer 3, and ARR is 6399. Now it's time to do master slave configurations. These are the configurations for first master slave relation, where timer 3 is master and timer 1 is a slave. And these are configurations for second master slave relation, where timer 1 is master and timer 3 is a slave. In the first master slave relation, first we specify how trigger output is generated in timer 3, which is master timer. I want update event to be trigger output, so MMS bits has to be 010. Here I configured MMS bits in CR2 register to be 010. Next I have to specify where trigger input for a slave timer is coming from. It's coming from timer 3, so TS bits in SMCR register in timer 1 has to be 010. Here I did that. In timer 1 in SMCR register, first I cleared TS bits and then I set bit 1 of TS. Next I have to specify what trigger input is going to do in a slave timer, timer 1. I want external clock mode 1 and 3 bits of SMS in SMCR register have to be set. I did that here. In the second master slave relation, first I have to specify how trigger output is generated in master timer. Here timer 1. I want enable signal to be the trigger output of timer 1, so MMS bits has to be 001 in CR2 register in timer 1. Here I did that. Next, where trigger input for a slave timer is coming from. It's coming from timer 1, so TR bits in SMCR register in timer 3 has to be 000. Here I did that. Next, what trigger input is going to do in a slave timer, timer 3. I want a slave mode selection to be in gated mode, so SMS bits has to be 101 in timer 3 SMCR register. Here I did that. Go in stepper start function. This function is going to have another input of type uint8t, I name it Q. Its number of total rotations. And another input of type uint16t, I named it R. It's the reminder of rotations. I have to write Q in timer 1 RCR register. Because this register is preloaded, I have to generate an update event, so Q value is stored in RCR register. In timer 1, in EGR register, I write timer EGR UG. This line is going to create an update event in timer 1. So Q value is going to store in RCR register. Next I have to write reminder in timer 1 CNT register. And after that timer 1 has to be enabled. Timer 1 CR1 register bitwise or assignment timer CR1 CEN bit. By setting CEN bit in CR1 register, timer 1 is enabled. I put this line after I enable timer 3 counter. Compile the code. There are 2 errors. We have to also correct the declaration of this function. Compile again. We have added some input argument to stepper start function, so the calls that I did here are not valid anymore. First input is number of complete rotations. I want 1 rotation. Second input is reminder of pulses. I give 0. And third input is direction. For the next stepper start, I write the exact same thing. One rotation, no reminder, and direction is counterclockwise. Compile again. There is no error and warning. I want motor to rotate one time in clockwise direction and then rotate one time in counterclockwise direction. I don't need to use a stepper stop anymore. And this delay has to be a sufficient amount of time for a stepper motor to rotate one rotation. Pay attention, in a stepper start function, CPU is just going to start the operation, and CPU doesn't need to wait for this operation to finish. CPU is just going to start it and go on its way. Timer 1 and timer 3 are going to do the operation. Compile the code. This is the project. Load the code in the microcontroller. Pay attention to this motor shaft. One rotation in the clockwise direction and one rotation in the counterclockwise direction. But as you should remember, in the slide I said we have to store reminder -1 in timer 1 CNT register. But if I do that, there's gonna be a problem if there is no reminder, and reminder is 0. I comment this line and also this line. Compile again. There is no error and warning. I load the code in microcontroller. As you can see, motor is not stopped after rotating one time. It's because reminder is 0, and when we subtract 1 from 0 and store the value in CNT register, that's when weird things happen. Here I write if R equals 0, R assignment 6400 and Q assignment Q minus 1. Compile again and load the code again. As you can see, motor rotated just one time. I reset the microcontroller just one time. Just one time. Just one time. Think about what I did and try to explain it. We can also test other values for rotation. If I want 1.5 complete rotation, first input is 1 and second input is 6400 divided by 1, which is 3200. Compile again and upload the code again. 1.5 rotation. I reset the microcontroller and you see it's going to rotate 1.5 rotation. 1/2. 1/2. Next thing is, how do I know operation is finished and motor stopped rotating? I can use timer 1 update interrupt for this. At the end of stepper init function, I paste these lines of code. In the first line, I clear update interrupt flag in status register in timer 1 peripheral. In the next line, I set UIE update interrupt enable bit in DIER register in timer 1 peripheral. With this line, I specify interrupt priority for timer 1 update interrupt in NVIC peripheral. And with this one, I enable timer 1 update interrupts in NVIC peripheral. Next step is writing the callback function. I write a function with return type of void. I name it stepper finish. Input argument is void. I have to specify this function as callback function for timer 1 update interrupt. I write address of this function in a specified function pointer variable. I write x callback timer 1. This is a structure. To access its members, you put dot after it. Its members are function pointer variables that are designed to store address of callback functions for timer 1 interrupts. I want to specify callback function for update interrupt, so I choose UP member. Then assignment, then I write address of a stepper finish function to this function pointer variable. Remember, name of a function is address of that function. To indicate motor is rotating, I want to use green LED on blue pill, which is connected to PC13. I want LED to light up whenever motor is rotating. So I have to add configuration for PC13 pin. At the start of stepper init function, I paste this code. In this line, I set IOPCEN bit in IPB2ENR register to enable GPIO C clock. And in these two lines, I config PC13 pin to be in output general purpose push-pull configuration. Next, I'm gonna write two macros for changing LED status. I'm gonna make a copy of these two macros and change them. And now I see I made a mistake in writing PR7 low macro. This macro is garbage and not doing anything useful, because instead of GPIO A BSRR register, it's changing GPIO B BSRR register. But the bigger question is why this macro being garbage didn't do anything to my code and my code worked correctly. It's because PO7 low macro is used when direction is clockwise. And that's where I use it in stepper start function, direction clockwise. The thing is, after PO7 configuration is done, PO7 output is low. So when this function is called and after that I use this macro, in spite of this macro not doing anything, because PO7 itself is now low, there wasn't no problem. But this macro can't make PO7 low. And if in this line I make PO7 high, now there's gonna be a problem, because this macro is not going to do anything about it. Compile again and load the code. Now you can see instead of rotating clockwise, the motor is going to rotate counterclockwise. As you can see, it's rotating counterclockwise. If I comment this line and I don't use PO7 high and compile the code and load it again, because PO7 output is low after config, now you can see motor can rotate clockwise. Now I'm going to correct this mistake, and this is going to be GPIO A BSRR. I'm gonna uncomment this line, compile the code and load it again, and now you can see motor is going to rotate clockwise. As you can see, it's rotating clockwise, in spite of this line being here or not. So back to what we're doing. I want two macros to changing LED status. Here I make a copy of these two lines. This is going to be GPIO C, this is BS13 and this is BR13. When I set PC13 output high, LED is going to be turned off. Here I write LED off. When I make PC13 output low, LED is going to be on. Here I write LED on. Compile again. Remember, in stepper init function, after you're doing PC13 configuration, turn off the LED by this macro. I want LED to be turned on whenever motor is rotating. So when stepper start function is called, I turn LED on with this macro. And whenever update interrupt for timer 1 happens and stepper finish is called, I want make LED off. Now compile the code and run the code. Pay attention to this green LED. So motor started rotating and green LED is not turned on. Can you guess why? The reason for LED not to be turned on is this line here. If I comment this and compile the code again and load it again, you can see LED is going to be turned on. As you can see, green LED is turned on. But why this happened? What happens in stepper start function? First LED is on. Then when this line is getting executed, an update event happens in timer 1. And then update interrupt happens in timer 1. And then stepper finish function is called and LED is going to be turned off. Before generating an update event in timer 1, I have to disable the interrupt and also clearing its flag. I use the line that I wrote here. I copy these two lines. In the start of this function, I don't need to clear the flag, I just need to disable the interrupt. I disable update interrupt for timer 1. And then before I enable both timer 3 and timer 1, first I clear flag in a status register for update interrupt for timer 1 and then I enable its interrupt. Compile the code again and load it again. You can see LED is going to be turned on whenever motor is rotating. LED is turned on and off. Whenever motor is rotating, LED is going to be turned on. I reset the microcontroller. LED is turned on and motor is rotating. Motor is stopped and LED is off. So how many pulses we are able to generate with this method? Now it's around 1.6 million pulses, which gives us 256 complete shaft rotation, and it is much less than the maximum amount of pulses that I can count with this method. ARR is a 16-bit register with maximum value of 65,535, and I'm using less than 10% of its capacity. I thought it is kinda nice to be able to write number of complete shaft rotation in RCR register without need to do any calculations. But if I write maximum value in ARR register, each time CNT counts from ARR to 0, it is 65,536 pulses, which is more than 10 rotation. And repetition counter counts number of timer 1 CNT underflows and can count from 255 to 0. So total number of pulses is going to be 256 times 65,536, which is around 17 million pulses, which gives us around 2,600 complete rotations. Now RCR register value is going to be Q, which is number of pulses divided by 65,536. And remainder of this division is R, and I write R minus 1 in CNT, except when R is 0 and conditions are Q is less than 256 because RCR is an 8-bit register and R is less than 65,536 because CNT is a 16-bit register and we are using the whole range. So let's go implement this and extend our range. First we go to stepper init function and timer 1 ARR, it's going to be 65,535, its maximum value. Next I go to stepper start function. Now its function is going to have two inputs. First input is going to be named pulse and it's the number of pulse that I want in timer 1 channel 1 output. At the start of this function I define a variable of type uint 8t, I name it Q. Other variable of type uint 16t, I name it R. Q is going to be number of pulses divided by 65,535 and R is going to be remainder of this division. This has to be 6 and this is also has to be 6. In this if R equals 0, then R has to be 65,536 and Q has to be Q minus 1. Correct the declaration of this function and compiling the code. Here I called a stepper start function. Now it's just have two input. If the first input is 3200, it means I just want a half rotation. Compile again, load the code. As you can see, it rotates half of a rotation. Half rotation. If I want 2.5 rotation, 2.5 times 6,400 is going to be 60,000. So the first input is going to be 60,000. Compile the code and load the code. 1, 2, half. 1, 2, half. If I want 3.5 rotation, I should give first input of this function 22,400. Compile again and load the code. 1, 2, 3, half. If I reset the macro, 1, 2, 3, half. Next question is, can we count more pulses? And the answer is yes. The problem is, how can we count timer 3 update event output trigger and stop timer 3 after it outputs a specified number of pulses? First solution was using one timer with 16-bit counter. I can use advanced timer without using RCR or using a general purpose timer without RCR. Now CNT can count from its maximum value to 0, which gives us 65,536 pulses divided by 6,400, giving us 10.2 shaft rotation, which is not enough. Second solution is using a 32-bit timer instead of a 16-bit timer. This kind of timers are not available in my MCU. In STM32F4 series, you can use timer 2 or timer 5. These timers have 32-bit CNT and ARR registers. Now CNT can count from its maximum value to 0, which gives us 2 to the power of 32 pulses. It is 671,088 complete shaft rotations. In the first two solutions, I am using one timer with one counter. In the next solution, I am using one timer which is an advanced timer and has two counters, 16-bit CNT and 8-bit RCR. This is the method that I implemented just now and it gives us 16 million pulses, which gives us 2,621 complete shaft rotations. But am I able to count more pulses than 16 million? The answer is yes. Instead of using one timer with two counter to count timer 3 update event trigger output pulses, I can use two timer. I'm gonna explore this method in another video. This is doable in STM32F103C8. And this method gives us 671,088 complete rotations. In this method, I'm using two general purpose timers, timer 2 and timer 4. But instead of timer 4, I can use timer 1. In this method, I'm counting timer 3 update event trigger output pulses with two timers and three counters, because timer 1 has 2 counter. This method gives us this amount of complete shaft rotation. There is also the possibility of using all the timers we have in STM32F103C8. This method gives us this amount of complete shaft rotations.